Alright, let's take a look at covalent bonding. In the previous video, we took a look at ionic bonding, and ionic bonding was the sharing of electrons between metals and non-metals. So ionic was it's actually not the sharing, sorry, it's the giving of electrons from a metal to a non-metal. So ionic bonding was the giving of electrons from a metal to a non-metal. Why would the metals want to give their electrons away to non-metals? Well, metals are on the left side of the periodic table, right? So they're either in groups 1 or 2. Now, what's notable at groups 1 or 2? Remember, the group number tells us the number of electrons in their outermost shell, so the number of valence electrons. Groups 1 or 2 are going to have 1 or 2 valence electrons. So it's going to be, they're going to want to get rid of them for a full outer shell, right? Because it's going to be easier to get rid of 1 or 2 electrons than to receive 7 or 6 new electrons, right? So metals want to get rid of their electrons, and non-metals want to receive new electrons because they're on the right side of the table. So in ionic bonding, the metals want to give away electrons and non-metals want to receive electrons. So it's going to be a perfect symbiotic relationship between the two because they both have things that they want. However, covalent bonding is between non-metals and non-metals. Non-metals and non-metals. Okay, it's the same thing. Why would covalent bonding be between non-metals and non-metals? Well, ionic was from metals to non-metals, right? So metals had something to give away and non-metals had something that they wanted that metals were giving away for free, right? Covalent bonding is from non-metals to non-metals because non-metals have a lot of electrons that they already have, right? So they don't want to lose electrons. They want to receive new electrons. So if you have two non-metals together, none of them are going to want to give away their electrons because they already have a ton of electrons that they've already got. They don't want to lose them. So covalent bonding allows these non-metals to bond together without losing electrons. They're allowed to share electrons. So what covalent bonding is, it is the sharing of electrons. It's not the giving like ionic bonding where an electron is actually given to another atom. It's the sharing of electrons. So you're not actually giving your electrons away, you're actually just sharing them. How would this work? Let's take an example with chlorine. Chlorine, if you look at chlorine in the periodic table, you're going to find chlorine has a mass number of 35.5 and an atomic number of 17. Now this tells us that chlorine has 17 electrons. So the first shell is going to hold 2, second shell is going to hold 8, right? And anything after the second shell can hold 8. So 8 plus 2 is 10. So the third shell, the final outermost shell, is going to hold 7 electrons. Now in this example, I'm only going to draw the outermost shell. In your exams, it'll probably only ask you for the outermost shell too, because drawing the innermost shell is probably a waste of time. So if we draw a chlorine atom, it's going to have 7 electrons in its outermost shell. 5, 6, 7. 7 electrons, right? Now these are called dot and cross diagrams. Why is it called dot and cross diagrams? You'll realize in just a second. And now we have another chlorine atom. Because this chlorine atom currently has 7 outermost electrons, right? Valence electrons. If it could bond with just another chlorine atom, remember chlorine is a non-metal by the way, with just another chlorine atom, this is also going to have 7 outermost electrons, right? 1, 2, 3, 4, 5, 6, 7. So this is why it's called a dot and cross diagram. We express one atom with dots, so the dots show the electrons, and another atom with the crosses. And this allows us to see the movement of electrons or the structure of electrons. So one chlorine atom has 7 electrons, another chlorine atom has 7 electrons. And this right here, where electrons are shared between the two, this is called a covalent bond. Where electrons are shared between the two, they're not actually given. So when you did ionic bonding, the metals and non-metals will actually gain charges. The metal would become a positive ion. Remember, ion is just a word for when an atom gains a charge. Metal would become a positive ion because it's giving away its negative electrons, right? And non-metal would become a negative ion because it's receiving these negative electrons. But covalent bonds, they don't gain charges because you're not actually giving or receiving any electrons. You're just sharing them between other atoms. So this covalent bond allows electrons to be shared between non-metals. That's important, non-metals. Because it doesn't happen from metals to non-metals or vice versa. Because metals and non-metals, metals want to give away electrons. Both these non-metals, they want to receive electrons. That's why this covalent bond works. And remember, they don't gain any charges. So, this is the dot and cross diagram. But we can show the covalent bond of chlorine in another way too. It's called a displayed formula. Displayed formula sounds all confusing, right? This is all it is. That's it. What does this mean? It means we're just going to have 2 chlorine atoms, right? And they're bonding covalently as shown by this dash. We're just getting rid of all these electrons and we're just replacing that with just a dash showing that these 2 chlorine atoms have bonded covalently. Now, why would you use covalent displayed formulas? Well, first of all, it saves time, and it's a much more simpler way to show these covalent bonds, right? But it comes with 2 major downsides. Number one, we can't see these electrons, so we're not able to see the structure of how these electrons or how they're shared. And number two, it doesn't tell us the 3D shape of the molecule. We can't tell what the 3D shape, like the physical 3D model, what it would look like. And for that, we would use a 3D model. We'll take a look at a 3D model with our next example. Okay, so let's take a look at ammonia. So in your GCSE exams, it might ask you to draw the covalent, show the covalent bond of ammonia. If you know ammonia is actually, the chemical formula of ammonia is NH3. So we have one nitrogen atom and 3 hydrogen atoms. So if you take a look at the periodic table, which you are provided in your GCSE exams, you'll find nitrogen has 14 as a mass number and 7 atomic numbers. And hydrogen has 1 and 1 for each mass number and atomic number respectively. Remember, the atomic number tells us the number of protons, but unless the atom is charged, the number of protons and electrons are equal. So this nitrogen atom is going to have 7 electrons and hydrogen is going to have 1. So if we draw a dot and cross diagram for nitrogen, we're only going to draw the outermost shell, by the way. So the first shell is going to hold 2, so the second shell should hold 5, right? So 1, 2, 3, 4, 5. And hydrogen, we have 3 hydrogen atoms, right? So we're going to throw 3 hydrogen atoms and 1 on each. And we're going to show the hydrogen atoms with a dot so that we can show how these electrons move between the hydrogen and the nitrogen atoms. Now, we have this nitrogen atom here, which needs 3 more electrons to have a full outer shell of electrons. It has 3 sides without 4 electrons. This hydrogen, well, remember, hydrogen, this is its first shell. It only has 1 electron. So it just needs 1 more electron to have a full outer shell. Well, each of these hydrogen atoms, think about it. It could fit into each of these sides of nitrogens so that they could all have full outer shells. Let's see what this would look like. Nitrogen, these 2 electrons are already full, and we already have 1, 2, and 3, so it needs 3 more new electrons. Well, it could covalently bond with hydrogen over here, another hydrogen over here, and another hydrogen over here. And remember, each hydrogen has 1 electron in its outermost shell, so it's going to covalently bond like so. So each hydrogen atom is going to have 2 electrons, letting it have a full outer shell, and each nitrogen atom is going to have 8 electrons, as seen by these 3 hydrogen atoms coming in and giving 1 and donating 1 electron each. So this nitrogen atom is also going to have a full outer shell because it's going to have 8 electrons out of its possible 8. This is a covalent bond. Now let's take a look at what its displayed formula is going to look like. Well, we're just going to get rid of all these electrons surrounding it, and we're just going to write out their formula, NHH. All bonding like so, right? And we draw dashes to show that they're covalently bonding. That's the displayed formula of ammonia covalently bonding. What would the 3D model look like? Let's say we just theoretically want to see how this looks like in real life. Well, we're going to have nitrogen atom, and we're going to have a hydrogen atom bonding to the nitrogen atom. 3 hydrogens bonding to 1 nitrogen. You're not expected to know how to draw these 3D formulas. You don't need to do that. You just need to know that if it comes up in your exams, you just need to know that what this 3D model is, and you just need to know how to read it. That's all you have to know. Now, covalent bonds create different types of substances too. Remember, we took a look at chlorine, right? 2 chlorine atoms bonding together, and ammonia, 1 nitrogen and 3 hydrogen atoms bonding together. These are all called simple molecular structures. Simple molecular structures. Why are they called simple molecular structures? Well, it's pretty easy. They're all molecules, right? Molecules are just 2 or more atoms bonded together, and each of them are 2 or more atoms. So they're all molecular structures because it's the structure of these molecules bonded together, and they're all simple. Why are they simple? Because it's just a bunch of these atoms bonded together. But there's an issue. We have these 2 chlorine atoms, right? And between them, they have strong covalent bonds. Same with this ammonia atom. We have strong covalent bonds between each of these atoms, forming one strong covalently bonded molecule, right? Simple molecular structures. But in between these structures, if we have another chlorine atom, chlorine molecular structure here, there are weak intermolecular forces. So these are the intermolecular forces between these molecules, right? And they have weak intermolecular forces. This means that although each chlorine molecular structure has strong covalent bonds bonding each of the atoms together, between these structures, there are weak intermolecular forces that can easily be broken. That's why covalent bonds aren't very strong. Although each of these covalent bonds between the atoms are strong, the intermolecular forces are weak. That's why they can be broken down easily. Let's take a look at some other examples of simple molecular structures that you probably should know. One notable one is H2O, water. You all know that, right? And another one is methane, CH4. CH4 is methane, H2O is water. And that's pretty much all you have to know about simple molecular structures, and covalent bonding. In the next video, we'll look at some properties of simple molecular structures, and I'll see you guys in the next video.